So, in this video, we're going to go over one last application of Hess's law. So, first of all, a little review. Already we've seen Hess's law applied to standard reactions. All right. So, what this allows us to do is that if we know the enthalpies of individual reactions, and we can arrange them so that essentially you add these two reactions together, and when you add the two reactions together, you just cancel the things out that are across from each other. So things that are on a reactant, a product side of one would cancel with the reactant side of another. We can see that half of the O2s would cancel out. So we cancel out this guy right here. That would leave half of an O2 right here. And we could just bring down everything that doesn't cancel out. And so if we know the enthalpies for these two reactions, we know that the sum of those will give us the enthalpy of this third reaction. All right, and again, this should be a review of having seen this before. So we later went on to apply Hess's law to this concept of energy cycles, all right, which is where we were taking an overall process, something like the dissolving of an ionic compound in water, and we were breaking it down into the individual steps. All right, so for example, when you dissolve an ionic compound in water, you could break that down into individual steps. Excuse me. First of all, of the ions breaking apart into gaseous individual ions, and then those gaseous individual ions becoming dissolved in water, and that would be the enthalpy of the first one would be the lattice energy, which is an enthalpy, and the second one would be the enthalpy of hydration, and the sum of those is going to be the enthalpy of solvation, which is what the overall process is. All right. So hopefully you're familiar with this concept of if you can add up individual steps that add up to another reaction, that if you can just sum those enthalpies and you get the enthalpy of the final product. Okay, so what we're going to do here is we're going to apply that strategy to one last concept, and that is bond enthalpies. All right, so if you recall from an earlier discussion that we had, we introduced this concept of bond enthalpy. And bond enthalpy is either the energy released when a bond is formed, all right, or it's the energy that is required to break a bond. All right, and these would just be opposite processes of each other. All right, so for example, let's pretend we're just talking about this one individual bond right here. All right, and again, this would not right here exist by itself, but we're just doing that to focus on the breaking of a bond between a carbon atom and a hydrogen atom. All right, so so whenever you break a bond, that requires energy. All right, so the energy required would be 414 kilojoules per mole of these bonds right here. All right, is there any such thing as a mole of these bonds sitting around? No. What that means is if we did this to, if somehow we were able to have 6.02 times 10 to the 23rd of these bonds, all right, and we wanted to break that many of those, that's how much energy would be released. All right, so we could also express this as the opposite of that, where we take these two things and we say, let's let these two atoms form a bond. All right, and when bonds are formed, we release energy. All right, and notice that these are just the opposites of each other. One is the energy required to break apart. The other is the energy released when the bond is formed. All right, so what we can do though is, so we have information on a bunch of types of these bonds, and these bond enthalpies are found in table 11 of your data booklet. So these are all for single bonds right here. For example, if we needed to know a carbon iodine, all right, what this would indicate, you just follow the chart across, that means that it would take 228 kilojoules per mole to break that bond. All right, so if we have multiple bonds, we can find those values down here. So for example, an oxygen double bond would be 498 kilojoules required to break that bond. So the strategy that we're going to use here is essentially we're going to, number one, calculate the energy required to break all the atoms apart into individual atoms, and then calculate the amount of energy that would be released if we allowed all those individual atoms to recombine to make the product molecules. All right, so let's show that with a sample reaction. And the reaction that we're going to do is this one right here. All right, so we have a little bit of information about this because this is the combustion of hydrogen. All right, hydrogen will, when combined with water, will give water, and hydrogen combined with oxygen will give water. And we have information about this because we have enthalpies of combustion. So if we look at table 13 in the data booklet, you'll notice that they list a value for the enthalpy of combustion of hydrogen. All right, and so that value is given right here. But one thing you need to remember is that these numbers are per 1 mole of whatever the molecule is that's being combusted. All right, so this would be for a reaction when you have 1 mole, or 1 as a coefficient in front of the hydrogen. Well, taking a look at our balanced equation, we have 2 in front of the hydrogen. All right, so for that value that we just pulled out of the data table, all right, notice that would be for this reaction right here, because if we make that per 1 mole, we have to have half of an O2, and that's going to give 1 molecule of oxygen. So if we want to know the amount of heat given off by this particular reaction, we have to double that. All right, so that's why I doubled that, and that would be, this enthalpy would be for this reaction as written. All right, so what we're going to do is we're going to compare this number right here, which would be the actual amount of heat given off by this reaction, to a value that we could calculate through this bond enthalpy strategy. All right, so essentially, a way that you can, just a crude way of putting it is we're going to first take all the starting molecules and we're going to rip them all apart. All right, we're going to rip them all apart to give these individual atoms. All right, so we can just kind of consider this to be, an imaginary box of atoms. All right, that we made from ripping all these guys apart. All right, and that takes a certain amount of energy, and we're going to be able to calculate that. All right, and then what we're going to do is we're going to take all those individual atoms and we're going to allow them to reform bonds to create the product molecules. All right, and when those bonds form, a certain amount of energy is going to be released. All right, so the overall enthalpy change of this reaction is just going to be a combination of those two processes. All right, because this right here is, you could kind of think of it as, the overall process is the same as if you broke all of the bonds to give individual atoms, and then you just recombined them to make the product molecules. All right, so let's see what we have here. If we look at the starting molecules right here, you'll see that if we get 2 of these guys right here, that would require the breaking of 2 hydrogen-hydrogen single bonds. All right, we got 1 oxygen, so we got to break 1 oxygen-oxygen double bond. All right, and we can calculate that. So again, these numbers right here come from the bond enthalpy chart that you saw previously. All right, so if we wanted to calculate a value right there, this right here represents the total amount of energy required to rip all these atoms apart into all these molecules apart into their individual atoms. All right, now let's figure out what we need to do here. We need to let these guys reform, and so what are the bonds formed? We're going to have a total of 1, 2, 3, 4 oxygen to hydrogen single bonds. All right, so the total amount of energy released is going to be 4 times that, which would be this value right here. So if it takes this much energy to rip them apart, but you give off this much energy when they reform, what's the total amount of enthalpy of the reaction? It's just going to be the sum of these 2 right here. All right, so we could calculate that would be minus 482 kilojoules. And just by comparison, this is the actual amount, and this would be the calculated amount from the bond enthalpies. All right, and notice that they're not going to be the exact same reaction or exact same value. And the reason for that is that all of the bonds here are average bonds. All right, actually these right here would be actual ones because there's only 1 molecule that's got a hydrogen-hydrogen single bond. Same thing here, only one molecule, molecular oxygen, which would have this. But an oxygen-hydrogen bond, for example, you can have that in water, but you could also have that in an alcohol. You also have it in a carboxylic acid. All right, and those oxygen-hydrogen bonds are different from each other. All right, so this value right here is an average for all types of oxygen-hydrogen bonds that you would find in molecules. And that's why there's going to be a disparity, because this value is calculated for an average oxygen-hydrogen bond, whereas this value right here is calculated for a very specific, it's specifically talking about the oxygen-hydrogen bonds that are in water molecules. All right, so why can we apply Hess's law to this? All right, it's a little easier if you see this represented in something that's a little bit more familiar to the Hess's law type strategies, where we represented it as reactions and we crossed things out and we tried to get them to add up to something. All right, so if you notice what we did here, we took two hydrogens and we broke them apart. All right, so I could represent it this way right here. We also took one oxygen, we ripped it apart. I could represent it like that. And in the end, we took all of these individual atoms and we put them together to make two water molecules, and I could represent that as this last reaction right here. So notice this right here would cancel out this right here. These oxygens cancel out over here. And we just bring down everything that's still on the left. We bring down everything that's still on the right, which would just be this right here. And that's exactly what we've been doing in all of the Hess's law problems. We just say that, well, if these guys sum together give this, we just have to add together their enthalpies and we would get that product. All right, so let's do one more example here. All right, how about the combustion of methanol if we calculated that by bond enthalpies? All right, well, we can, I'll skim over this. We can figure out what the actual enthalpy is. The actual enthalpy would be this value right here. And we get that from going to the data table and finding, looking up the combustion enthalpies. We find for methanol, it would be this value right here. All right, and remember that's per 1 mole of methanol. So since this balanced reaction right here actually contains 2 moles, we have to double that. All right, so make sure that you make that consistent with whatever your actual reaction is. All right, so let's do it with bond enthalpies. All right, well, if I take this reaction right here and I represent it just with Lewis structures so that I can see the actual types of bonds that are in those molecules, we can see that in this molecule right here, we have 3 CH bonds, we have 1 carbon-oxygen bond, and we've got 1 OH bond. All right, but the thing is, we have 2 of these molecules right here. There's 2 of those. All right, so when we add up all of those, the grand total of CH bonds, since we've got 2 of these molecules and we've got 3 CH bonds, that's a total of 6 CH bonds that we need to break. All right, so we can calculate that right here. We would have, with those 2 molecules, we have 2 COs, that would be this. The 2 OHs would be this right here. We can calculate a sum total of breaking apart 2 of these, that would be this. All right, we've got 3 of these oxygen molecules. We can very easily calculate the amount of energy if 3 of those were ripped apart, that would be this, giving us a sum total of this value right here. That's the total amount of energy to tear all of these molecules apart to their individual atoms. All right, so now we got to calculate how much energy would be given off if we rebuild these things. All right, we've got 2 carbon dioxides. Each of those contains 2 CO bonds, so that's a total of 4 carbon-oxygen bonds. So that's what we would have right here. So that would give this value. If you get 4 water molecules, that makes a total of 8 OH bonds. All right, and each one is 463. All right, so we calculate, that would give us this. We add those together, and that makes up this number right here. Notice that this is a positive value because that's energy required to break bonds, but this is a negative value because that's energy released when you put bonds together. All right, so adding those together gives us this value right here. All right, and notice again, it's different from the actual measured value, and that's because it's done from average bonds.